Thank you very much. Thanks for the opportunity to speak today. And so, yeah, this will be a quick overview of NOAA's activities with the Global Hawk aircraft as applied to high-impact weather. And it takes a large team to make anything with the Global Hawk happen, and certainly our work is the same. So I want to acknowledge the large set of people who have contributed to this, and it's actually more names even. I'm drawing from material much beyond who's shown here. I'll begin with just a quick overview of the NOAA Unmanned Aircraft Systems program. It officially begun in 2007, but activities had started before that, going back to 2005, a demonstration with the Altair, a Predator-type aircraft over the Pacific. The goals of the program are really to evaluate the utility of UAS for NOAA operations and research. Will it make a good contribution to our current observing system? We're focusing on 3 areas right now: high-impact weather, which I'll be speaking about; marine monitoring, which Todd Jacobs will speak about in a different session this afternoon; and then also Arctic research. We're looking at a wide range of platforms, but what I'm going to talk about today is our use of the NASA Global Hawk. And so NASA acquired 3 of the pre-production Global Hawk aircrafts early on and stood up 2 of those for flights. They've since acquired additional aircraft, but those aren't in a flight status yet. The Global Hawk, it's a high-altitude, long-endurance aircraft. It operates in a cruise climb mode where it quickly climbs to about 57,000 feet and then continues to climb up to altitudes of about 63,000 feet as it burns off fuel. NASA has demonstrated an endurance of up to about 28 hours, but typically in our missions we're usually flying maybe 24 to 26 hours in the missions with NASA. It can carry a large payload, so that's very nice: remote sensing instruments, dropsondes. What I'm going to be speaking about here for the bulk of our analysis, the bulk of the NOAA applications, are dropsondes, a dropsonde system developed by the National Center for Atmospheric Research with funding from NOAA. And so the Global Hawk dropsondes, it's the same sensor package as on one of the manned aircraft, but it's in a miniature size. It weighs about a third of a pound, and the tube has a profile about the size of an empty paper towel roll. The Global Hawk has a dispenser which is mounted in the rear of the aircraft. This can carry 88 of the sondes, and then there are 8 channels, so we can have 8 sondes in the air at a given time. And so we can deploy quite rapidly, but we run out of channels. It means that at a sustained rate we can deploy about every 25 kilometers. And so then these of course give the high vertical resolution measurements of temperature, humidity, and wind speed. So NOAA has been involved with the NASA Global Hawk operations really from the very beginning. NOAA did contribute some funds to the standing up of the aircraft, and then we had scientific involvement through David Fahey in the very first mission, the Global Hawk Pacific mission in 2010. We played a role in the Genesis and Rapid Intensification Processes, or GRIP mission, in 2010, which was the first time the Global Hawk flew over the top of a tropical cyclone and hurricane. We would have liked to have played a bigger role. Our dropsonde system wasn't quite ready at that time, but we then were able to come back in 2011 with a NOAA-led mission, the Winter Storms and Pacific Atmospheric Rivers mission, where we had the first dropsonde release from the Global Hawk aircraft, and I'll say a little bit about some of the science results from that in a moment. We then participated in the NASA Hurricane and Severe Storm Sentinel mission. We just finished the third of 3 deployment years this past year, looking at tropical cyclones. I'll again share some results from that. And then other people from NOAA have also been involved in another mission, the ATREX, or Airborne Tropical Tropopause mission. So, a great collaboration, I think, between NASA and NOAA, and we want to keep that going. So the Winter Storms, Pacific Atmospheric Rivers experiment, a NOAA-led mission, the main goal was to really demonstrate the operation of the dropsonde system and look at how it could potentially be used operationally. But we had 3 flight opportunities which enabled us to do some science related to atmospheric rivers, winter storms, and then also Arctic weather. And we were fortunate on each of the flights to sample an atmospheric river. And so the first result that I want to highlight is from these sampling of the atmospheric rivers. This is the very first flight that we flew, where we were able to get a couple of transects across this atmospheric river, as reflected by total column water vapor satellite imagery there. We had hoped to get a couple more transects, but we had an issue with the aircraft, had to return early. And with these, what we're showing is this is observations from the Global Hawk. This is contours of the water vapor transport within these atmospheric rivers. And there was a session on this just yesterday. These are a major supplier of moisture to the Pacific West Coast. And so these observations were very valuable to then go and look at the various different reanalyses, CFSR, MERA, ERA interim, evaluate how well these different analyses are able to capture the representation of these atmospheric river events. And Marty Ralph has a paper in preparation on this, and then I'll also be presenting a poster tomorrow afternoon. So I encourage you to go by and take a look at that for some more information on our analyses of atmospheric rivers. We had a flight during that campaign up to the Arctic. We flew up to 85 north, had a drop, clear up at 85 north, and then on the return, we were able to do a line of drop sondes just north of Barrow. And so what is shown here, these are contours of the observations, temperature, specific humidity, wind speed, and the wind direction. And then we have some comparisons underway with two of the drop sondes, a radio sonde from Barrow at one point in time, and then profiles from the ERA interim analysis. So this is the total column. This is an expansion of just the lowest level. And the basic message here is by being able to deploy these sondes in rapid succession, we get a much better representation of the variability in this region that a single radio sonde or the atmospheric reanalyses can't describe. And so Janet Intrieri just led a paper that came out just this past month or so in atmospheric measurement techniques. If we turn now to hurricanes and the Hurricane and Severe Storm Sentinel mission, I think this graphic compiled by NASA really hits home why we're interested in using the Global Hawk aircraft. So this is a culmination of all the flights that were flown over the 3 deployment years of HS3. And so you see that with this aircraft, we were really able to sample just about any part of the North Atlantic Ocean and do so with some significant time on station. So an amazing potential addition to our observing system capability. So within NOAA and with the drop sondes, one of our key priorities through our participation in HS3 was getting data out to the operational parts of NOAA in real time, to the Weather Service and to the National Hurricane Center. And so up above, just show a sample of the display that we would get from a real-time mission monitor within the system. And so as we would go along, each of these blue dots represents a location where a drop sonde was deployed. Through participation from the NOAA Hurricane Research Division, they're working up the data in real time. And then if you actually, within the real-time monitor, if you clicked on one of those dots, then you could see the SKU-T data, and all of this was flowing through the operational data portal. And so as a result, forecasters with the National Hurricane Center were looking at the data, and this is an example from one of their discussions going back to 2012, where they were using the data from the flights in real time to help guide some of their discussions and their input. This past year, one of the highlights was sampling of Edouard. We had 4 flights into the various stages there. And again, these data were getting to the National Hurricane Center, and it actually caused some discussions there of whether they actually believed the data. We were at a point where the storm was rapidly intensifying. Their first instinct was no, the data probably isn't right. But in retrospect, looking at the various satellite analyses, it did hold true, and so the data, again, are making it all the way through. Within NOAA, one of our key things, again, is then how are these data sets impacting the forecasts? And so this is a slide from Jim Doyle at the Naval Research Laboratory. He showed this in a session on Monday. And so this is looking at, in the Navy COAMPS TC model, looking at what the impact of the drop sondes from the Global Hawk are on the forecast accuracy. So the upper left panel is a measure of track error. In each of these are errors. Lower is better. On the right, 2 measures of intensity, maximum wind speed, minimum sea level pressure. And in each case for this event, we're seeing a very significant reduction in the errors with the inclusion of the drop sondes from the Global Hawk. So this is extremely encouraging and one of our motivations for continuing this activity. And Jim showed some recent results from the Edouard flight as well, which were maybe a little bit more mixed, but still in general demonstrating a positive impact. We're, of course, then also interested in how this is having an impact on the operational NOAA models. So this is work by Vijay Talapagrada at NCEP using the operational HWARF, or Weather Research and Forecasting Models for hurricanes. And in this study, he looked at it at a variety of different situations, but I really want to call your attention to these lower two assimilation experiments where there was the assimilation of global Hawk dropsondes, first in a base configuration, and then a second one with reduced observational errors. So we're going to be comparing these two experiments with assimilation of the dropsondes with the control case, which assimilated other observations. So these are results from Hurricane Nadine flights in 2012. And so what we're looking at is a comparison of the red and purple with the blue trace. These are again measures of error. So this is track error in the upper left, minimum center pressure, and maximum wind speed. And so we're again seeing with these inclusion of dropsondes, we're seeing a significant improvement in track forecast in this case. As we turn to intensity, a little more mixed. We're seeing a reduction in the errors over the near term, out to about 36 hours, but then we actually see something of a degradation of the forecast at longer time periods, and relatively little impact on sea level pressure. That's one instance. If we turn to another one of Hurricane Humberto the following year, in this case, a neutral impact on track forecasts, but we are seeing some significant positive impacts on intensity and sea level pressure. So it's a complicated situation, but in general, all these initial impact studies really are demonstrating that these data could have a significant impact for NOAA. Of course, the Global Hawk isn't flying just only dropsondes, a number of other payloads out there. A couple that we're particularly going to be looking at within NOAA are the Hamster. This is a passive microwave sounder by the Jet Propulsion Laboratory. Gives profiles of temperature and humidity similar to AMSU. The HIRAP, this is a Doppler precipitation radar from Goddard at NASA, giving maps of wind speed, three-dimensional maps of wind speed and precipitation, and then also the HIRAD, an SFMR type radiometer giving measurements of wind speed over the surface. So what's next? Where we're going from here is we're to kind of move from these research type missions of NASA into a more operational evaluation. Look at specifically, can the Global Hawk impact NOAA forecasts? So we're starting up a program called SHOUT, Sensing Hazards with Operational Unmanned Technology, where its overall goal is to demonstrate whether these observations can reduce forecast error, and particularly do so in the context of a potential gap in satellite observations. So as part of that, we'll be conducting data impact studies, both data denial studies, observing system experiments or OSSEs, and the numerical OSSE or observing system simulation experiments. But then also as part of that, an equal part of the campaign will be a formal cost and operational benefit analyses to look at the economics of the whole thing. So 2015, this year we're on track to do another campaign studying Atlantic tropical cyclones. Again, focusing on the forecasts of track and intensity. We'll hopefully be flying from Wallops this August and September. We're budgeting 5 weeks of science flights. Payloads are likely to include the dropsondes, the microwave radiometer, and Doppler precipitation radar. We're hoping to have up to about 10 total flights. Moving to the following year, the schedule is a little less certain there, but we're targeting potential deployments to look at storms impacting Alaska, and also the winter storm type model. And so there we're looking at demonstrating improvements in forecast with respect to threats such as extreme precipitation and damaging winds, looking at forecasts out to 3 to 7 days. So our plans here are going to be a little bit dependent on Global Hawk availability, and we really want to have more guidance from these modeling studies to help demonstrate what sort of flight profiles and what sort of approach will have the maximum impact. So just to wrap up, I think through this collaboration between NOAA, NASA, and a number of other people, I think we've been able to demonstrate some of these initial capabilities in multiple cases. Preliminary impact assessments have been extremely positive and encourage us to go forward. Potential benefits include these extended observations in remote regions, guiding us to better warning capabilities and potentially address the satellite gap mitigation. And so then, just finally, we have a more formal evaluation of its operational impact underway. So thank you very much for your attention. I appreciate it.
Okay, thank you very much, Gary. We have time for a question. Brian?
So within HS3, I didn't speak to that, but there are actually 2 aircraft that were to be part of the campaign. One was the Environment, one was Overstorm. Very early on, it would have been a desire to fly both at the same time, but from permissions and then just the we weren't able to get to that point. NASA has demonstrated through a refueling campaign actually flying multiple Global Hawks at the same time, but we didn't actually get there.
Okay, one other quick question.
Hey, Gary, I was just wondering why you decided not to fly scanning HISS, which does a really nice job of making measurements in the environment around tropical storms, as opposed to the SONS, which have considerable
So there it's you know, and we're finalizing the instrument discussion, so these aren't formally announced and all of that. It really comes down to where the instruments are on the platform largely, and so we definitely wanted to have HIRAP out there, which unfortunately kind of conflicted with scanning his. So short answer, that's part of it. Real estate.